So today we talk about qubits, about quantum computing, things like that. It's very popular in Delft. What is the plan? I would like to talk a little bit about qubits as quantum units, about quantum computing in general. Perhaps you know already this information at very general level. Well, it belongs to quantum transport. That's why I could tell you about this. In my test, it's a bit mathematical. Then we will talk about a single qubit, and we will understand how to manipulate it. If it is physical, to some extent, because we will talk about a qubit, any two-level system can be manipulated in such a way using resonant fields. And one can also talk about multiple qubits, which is necessary for quantum computing, coupling between the two qubits, separating two qubits simultaneously, which is called quantum gates. So that will be rather general discussion, and more upon my test, rather useful. Then we will talk about practical realizations of the qubits in the context of systems which are studied in quantum transport. And mainly, I will talk about different kinds of Josephson qubits. I should say that Josephson qubit technology is quite developed by now, and not all the types I will list are actually used for modern qubits, but physics, which has been studied, which has been attempted to implement for this system, it was looking at, it was to understand how all this works. Eventually, that's a goal of physics, at least of technical physics, which you study. I will talk about realization of the qubits. And time allows, I will mention some spin qubits are also popular in Delft. Good, so let me talk about quantum mechanics in general. I would like to compare two-level systems, qubits, which are elementary quantum information units. I'd like to compare them to classical bits, classical information units. And what do we have? Classically, we have two states, and the system can be either 0 or 1. Using this concept, one can do wonders. One can make computations, and the computers play quite a big role in modern life. What is the difference if we have the same two states? And think about this quantum mechanics. Most important component of quantum mechanics is that it's always possible to arrange a superposition of these two states. let us count how much information a qubit can contain. If we talk about classical qubits, the information is just 1 bit, a unit of information. To describe a state of quantum bit, eventually we need two numbers which are coefficients of superpositions, two complex numbers. Well, there is, of course, normalization condition imposed on these two, and also common phase of these two numbers doesn't matter. So, in fact, the state of a qubit is given by two real numbers. It can be represented with a finite number of classical bits, say 64 bits is usually quite enough to present a float point number. Sure, it's already a little bit more information, but it's not all. If we want to present a state of n qubits, we would need much more bits, actually exponentially more. We see here 2 to the power n, which means that if you look at it formally, qubits are very much powerful memory units. It's a wealth of memory which one could, in principle, put into qubits. Since it grows exponentially, kind of what are examples like with 40 qubits, you can keep memory of all musics ever played by humankind. Numbers are really big. Now it looks like an application of quantum computing is kind of trivial, and why don't you just use qubits as memory blocks? That doesn't quite work, and you know that, at least you've been told about this. This information cannot be really read or written as you can do with classical memory, right? If you do measurement on a qubit, you collapse the wave function. So even if you have a single qubit, you're still, if you would like to measure these two numbers, you cannot do this. What you can measure, after all, it's either 0 or 1. One could have many qubits in the same state, make statistics of this measurement, and finally determine this too. But that's not what is available. So there is a problem with using this wealth of information, reading and writing to it. That's why quantum computing is not about using it as memory. It's about processing. For classical computing, it's kind of taken for granted that at any stage you can stop classical computer read all the state of the system, read all bits, and then interrupt the process and if necessary, continue the computation. It took a while to change the paradigm and to understand that one can actually process the information without writing or reading this. And this was the way to use this wealth of memory. Well, it was still a mathematical problem to prove that quantum computers can be more efficient in this processing, can be more efficient than the classical computer. This proof has been delivered in the 80s, like 30 years ago, and since then we have quite a glow of interest to quantum computing. Now we have first systems which are announced to work as quantum computers. Well, they're still very primitive and can hardly be implemented for practical purposes. Nevertheless, there's still a big drive. There's still it is still very popular direction to get the practical quantum computer to use this amounts of memory accumulated in qubits for practical purposes. Good. Let us describe the quantum computer, although it's not yet implemented in hardware. On paper, we have it. And let us understand how would they work. First of all, we have qubits. Qubits here are given by lines. And what happens here is time. We process information in time. Good. So we have some initial state. We have prepared this. This is a state of 5 qubits. And then we can change this wave function by unitary transformations, keeping quantum coherence. So, for instance, here we do something with subqubits. Here is first. Here it's an operation which is called quantum gate, and that involves 2 qubits. And well, one could just implement much bigger gates, accumulated information of all qubits. In any case, at least in paper, the state of the computer experiences ideal quantum evolution. Right, so the program runs, and at some stage you got output wave function. Now one has to read the result. One has to measure it. Measurement has happened, it gives a result, but again, in order to completely characterize this wave function, one measurement is not enough. So again, the computer is prepared to the same known initial state, the program runs, and the output is read again. So that's how people thought and think of practical implementation of quantum computer. What are requirements? What are requirements to put it into practice to realize this physically? First of all, one needs qubits. One needs physical systems, two-level systems, where quantum information can be stored. Second, one should be able to process this information. So there must be operations which will change the state of this qubit. It also has to be realized physically. Obviously, the information can be read. So these 3 points look pretty much straightforward, trivial. 2 more points. Fourth point is very critical, is a requirement of weak decoherence. Namely, it means that for the time the program runs, quantum program is executed, nor interaction of quantum computer with any other degrees of freedom should take place. So thousands of ways to do this. There might be dissipation, decoherence in these quantum systems, and this is a major block for the realization. So one needs to isolate the system from environment as good as possible. There are many ways, many tricks how to do this, and under them you have sufficient time to execute your quantum program. Okay, that's still physics. And the last point comes from the requirement that it has to be a practical, useful device. And that can be only achieved if you can operate many qubits simultaneously. Sorry, I should have said simultaneously. Many qubits within the same device. They have to talk to each other. And one should be able to design these devices. This all is called scalability. So just to make 2 qubits is not enough. One has to provide means to arrange these 2 qubits, these 40 other qubits, to make a system out of that. It is called scalability. Fine, there are requirements. Before I go on, I would like to answer the question which you have not actually asked, but well, at least in early times, students have asked this question frequently, and the question was when quantum computer will be available. Something that it will never happen, something that it will happen in a year or 2, so it doesn't make any sense to do, for instance, master project in this direction, because everything will be done very soon. I guess good answer is to recall the story of classical computer. And the story was like this: a classical computer has been invented in early of 19th century. Guess the first publications by Charles Babbage. First ideas were that early, and it was not really on paper. He actually wanted to build one. He got grants from British Navy to build a computer, and he had blueprints. However, that doesn't quite work at that time. That was mechanical computer. There were no electronics by the time. It all was collection of like a clockwork. And the technology of that time, unfortunately, could not supply sufficient accuracy for manufacturing the small details. So the idea of Charles Babbage had to wait till 120 years till people figure out how to use electronics and how to build up a classical computer with electronics. So that's a kind of typical time span at which good ideas are implemented in practice. Good. That was very general introduction. If there are any questions, please put it into chat. And I will, no questions, then I will talk about a qubit. And I would like to keep the discussion as general as possible, and it's quite plausible in the context of the qubits because they're simple. If you have a wave function which has only two components, and if you want to make a Hamiltonian which works with this wave function, it can only be a 2x2 matrix. Right. Any 2x2 matrix can be represented as a constant, and constant matrix, unity matrix is not really interesting here. It will only change the overall phase of the wave function. So any 2x2 matrix can be represented as a linear superposition of three Pauli matrices. You remember Pauli matrices used to represent electron spin, three components, and right, that's a kind of usual analogy. And a qubit can be regarded as a sort of electron spin, which is subject to three fields. Related, coupled to these Pauli matrices. For electron spin, those are three components of magnetic field. For other realizations of qubits, it can be, for instance, gate voltage and magnetic flux, many things. But this, the concept of these three handles is important. Right. It's also important that we can change these handles, these controls in time to manipulate the qubits. Let me describe a convenient representation of a qubit state. Let me get convenient form for this alpha and beta. Good. So this is the following form which is suggested to us. There are two angles which can be seen as the angles in spherical system of coordinates. So these two angles would define a point on the surface of a sphere. However, yeah, if I look at these expressions, they look strange. They don't look like usual vector components in the spherical coordinates. No wonder, because wave function is not a vector. What is a vector in this system is the average spin associated with this wave function. So if one computes average values of x, y, z component, it already makes sense. Those are components of a vector in this coordinate system. Good. So we can represent each state of a qubit as a point at the sphere. So there will be two states, basic states, and they will correspond to north pole and south pole at this sphere. Equal superposition of two states, like 0 plus 1 divided by normalization factor, would correspond to a point at the equator of a sphere. And so on. Each superposition finds this place. Right. So the state is a vector at this Bloch sphere. If you go from one state to another state, what you do, in fact, you rotate this state along the surface of the sphere. That's how qubits are manipulated. Good. Let's go through the stages. Stages are required for quantum computing. Let's first prepare the qubit in a certain state. Well, the simplest way to prepare is just wait a while. In any case, if you wait a while, all this decoherence process, all this dissipation process will have time to take place. And if, for instance, we have field B along that axis, that make these two states, basic states, different in energy. And if temperature is sufficiently low, if temperature is low, then the energy difference between these states, the system will go to ground state. Good. It is prepared in a certain state. If you don't like the state, just switch the direction of the field, the ground state will become state 1, and you can prepare your qubit observer. Fine. To understand how to change the state, let us first look at rotation with a pulse of effective magnetic field, or whatever these fields which are coupled to signal matrices. In that case, we start and we end up with a situation where all these fields are 0. All 3 components. Well, if we could do so, right? So sometimes you cannot just remove energy splitting in the qubit, and that also has a solution, but one needs to use resonant manipulation. But let us, for simplicity, first think of a qubit without energy splitting. The manipulation is quite simple. One just applies a pulse of a field for a certain time duration. And the pulse would make the spin of qubit would make it to rotate about this axis. In this case, we think of x-axis, so it will change the states in a perpendicular plane. Right, so one can elaborate and write down rotation matrix, which has a rotation angle. And what is a rotation angle? It's just the magnitude of the field times duration of the pulse. Right, so if initially in state 0, we will go to this state or superposition. What are particular values of this angle? Right, so for instance, if gamma is power 2, then we, let me sketch Bloch sphere quickly. Then we go, for instance, from the North Pole, rotation by power 2. We go to equator. So we have equal superposition of 2 states. Let us rotate it once again by power 2. In this case, we go from North Pole to South Pole. So we flip the state of the qubit. Right, let's go on. Let us try 2 pi. And if you think of this kind of normally, if you think about this, the spin which is rotated, you expect, of course, no change. It was at North Pole, and it comes to North Pole again. However, if you look at the correct representation of wave function, you can see that it actually has changed sign upon 2 pi rotation. And one gets identical wave function only if rotation is by the angle of 4 pi. Good. Rotations with a pulse. It's a simple And one can make any rotation over x-axis, or if one wishes over any other axis. Suppose we choose the rotation along that axis. What does it do to wave function? In this case, it does not change moduli of this alpha beta of this coefficients of the superposition, but it changes their phases, their mutual phase. That's why this rotation is called phase shift. So even if spin in this direction, and if you rotate this, right, something has changed. There's a phase shift accumulated for the state. Good. Now the point is that, yeah, at the abstract level, it is very convenient to think of degenerate levels, which are precisely the same energies, so all these handles are set to zero. But in practice, it is either impossible or inconvenient to do this. So we need to talk about qubits where there is an energy difference between the levels. How to manipulate those? Well, it appears to be not very difficult, and one could do the following. One can, in simple words, to compensate this energy difference with a proper frequency of the applied field. So instead of constant pulse, we will actually apply a pulse of radiation of oscillations, a train of oscillations, which will have a frequency matching the splitting of the levels. So how to see that this works? Kind of simplest and fastest way is to go to rotating frame. So it's a frame, it's like a system of coordinates. So we look at this function in a different coordinate system, which changes in time. Here is transformation. And the field, which was oscillating, upon changing of coordinate system, will become constant. All right, it will become constant. So we are back to the situation of pulse with this magnetic field being constant in time. Right, this is the basis of resonance manipulation. Everything is clear, or I managed to make you sleep? Oh, let's see. There's something in the chart which I have not seen. I've lost shut windows again. I need to stop share to see what's going on. Why there's a factor of 2 in gamma? Let us see, it was a previous transparency. In gamma. Let's see, I had answer. This one. Yeah, it's just definition of gamma. So in this case, gamma is not a phase which is acquired by wave function. Gamma is the angle at which spin is attached. So it's just a definition. One could use gamma here, and but then you would have gamma over 2 for the spin. Does this answer your question? Just a convenient definition. Oh, I'm losing chatting again. Okay, right. No, right. That's fine. Good. Let us see. It's already about break time. But yeah, I guess I can say a little bit more. And that was about single qubit. And I would like to talk about more because, well, qubits have to cooperate, have to be a part of quantum computer in order to provide quantum information. And a particular example of quantum gate, which involves only 2 qubits, is a CNOT gate. It has been proven at some stage that eventually for a universal quantum computer, you in principle need to realize only this gate. And you should be able to apply this gate to any pair of qubits, and then it will work. It is perhaps not the ideal practical implementation, but that gave people courage in a sense that if you realize this CNOT gate, you're in business. You can, in principle, think that you can make from the system under investigation a real quantum computer. That's why practical realization of this gate is so important. But let us understand what does it do. In CNOT gate, we have 2 qubits. One is first qubit is control qubit. And the second qubit, and control qubit does not change in the process of this manipulation. And the second qubit remains the same if control qubit is in 0 state. Yep. In all these situations, the state of second qubit also doesn't change. And if the state of control qubit is 1, then it does change. That's why why people call it so. CNOT means controlled NOT. So negation proceeds controllably. Good. That's still a classical description. One can make a classical gate which works like this. In order to make it quantum mechanical, one should be able to make a unitary matrix which corresponds to this process. Here it is, so one can check. So in this block, there's no state of change. In this block, the state is flipped. And the blocks, they differ by the state of the first qubit. So this is CNOT gate. Right. Let us understand now how two or more qubits can work together. Again, for two qubits, still no problem to arrange a Hamiltonian, which has terms of interaction between them. So there are Pauli matrices, spin components corresponding to two different qubits, and they are corresponding couplings, pairwise couplings. There are 6 possible couplings which can couple different components of these spins. Right, general Hamiltonian. And then how to operate two qubits. Well, the idea is again the same. One can make pulses of this k in time, and there will be a sort of rotation, but it won't be rotation of single qubit. It would be simultaneous rotation of two qubits along a certain axis. Right, so I have a little example of how to make a CNOT with such gates, but I think I will tell about it after the break. So I promised to make large breaks. Let's see. Let us meet in 12. Very good. So let me appear here again. Let me tell more about quantum gates. Basically, what I want to do, how people can make these gates using the elements which are given. For instance, people can, in a system, people can realize such an interaction between the qubits. So this is a coupling of X and I components of the chip in this basis. Well, how to figure out what will happen, one has to write as a matrix in 4x4 spaces, and then consider the change of the wave function when you apply a pulse of J in this form. This is the resulting matrix. So we did something in the central block. These states remain the same. It's not quite CNOT, but kind of problem of engineering, of mathematical modeling is to figure out how to make more sophisticated operations by combining these two, this gate and, for instance, single qubit rotations. So let me just show the answer how to realize such gate. The sequence of operations appear to be quite complex, but in any case, it's just only several operations, and if you do everything fast, you can make sufficiently fast the overall operation of CNOT. So what are here? There are single qubit rotations of either qubit 2 or qubit 1 along different axes. So here we have, for instance, that would bring it to equal superposition space. That would be phase shift. And then in the middle, we apply this interaction gate, actually twice. And the result of all this matrix multiplication will be CNOT. So in fact, as it is the case with classical computer, you can do everything from everything. It's just a matter of programming. Good. With this, let me concentrate on physical realizations of two-level systems. And again, as I promised, I don't want to talk about technology. I don't want to concentrate my outlining on the best qubits which are used. I will take the whole topic of Josephson qubits, which have been initiated in Delft by Professor Mori. And now Leo Di Carla is the person who does quite sophisticated things with Josephson qubits. There's still interest to spin qubits in Delft and QTech. There's also a section which makes spin qubits. There are different realizations of quantum bits, quantum computers. For instance, people who would like to do it with cold atoms that we don't look to. Any practical realization, yeah, I guess it's now it converges more or less to the Josephson qubits, to solid state qubits. Fine. Right, and let me first understand, refresh the lecture. What was that? Was it lecture number 7? A lecture about the Josephson quantum mechanics. So why can we use Josephson junction as an elementary quantum unit? Well, because it's just quantum mechanical. It has wave function, which can be written either in phase, or phase is the same as magnetic flux, or in charge representation. Right, so there are associated Hamiltonians, thus charging energy, which in phase space looks like kinetic energy of a particle. And there's Josephson energy, which in phase representation looks as a potential, where this particle is moving. Right, we also understood by that time that it depends on boundary conditions whether this system of equation, this equation describes a single junction, and then the wave function doesn't have to be periodic in phase, or a single island when it has to be periodic in phase, and then n is just discrete number. The charge is quantized in an island, while it is not quantized in a junction. Right. Having that, there are many ways to make. Okay, let me protect this. This is general Hamiltonian. This gives you some states, and in fact, you can arrange a qubit just picking up any pair of the states, right? That gives you really infinite number of possibilities. Some of them are practical, some of them practical, some are easy to make, some are difficult to make. So people have tried many different combinations, many different realizations. So let me start with what used to be called phase qubit. It is just single junction, no island. And how does it work? You might remember Washboard potential for Josephson junction. Let me quickly recall it. So energy versus phase. If current is applied to a junction, it looks like this. If the current is sufficiently big, there are no minima in this curve, it's just a smooth curve going down. If the current is very close to critical one, we can concentrate on a single minimum separated by a barrier, and we come to this plot. All right. So now we understand what plot is this about. Right. It's a quantum mechanical particle. It is in a potential well, and the states are approximately quantized. There's a ground state. There's a first excited state. There's a second excited state. And let me say the following. They're not really precise quantum mechanical states. Why is it so? Because if particles in certain state, there is a probability of tunneling. It goes over the barrier. And it goes all the way down. And we learned what has happened in this case. If it doesn't stop in the minimum, it means just that there is a voltage at the at the junction, the state has changed drastically. Well, it's too bad that the states we arranged don't live long, but it gives a convenient possibility to measure it, because you cannot miss this large voltage pulse. Good. So in this setup, which was made quite some time ago, in this setup, from these states, only 2 has been used as qubit states. Well, okay. It's obvious choice if you have so few. Let us see how one can achieve manipulation over there. It's a resonant manipulation. A little bit of drawback of this scheme is that we can modulate only current applied to the junction. We can slightly shake this potential. Only one parameter that we can change, but that's enough. That could provide resonant. If we do it at resonant frequency corresponding to the difference between these 2 levels, you're on business, you can provide coherent coupling between these 2 states, 0 and 1. Fine, that's common for all the qubits. What is less common, what is specifying trick implemented for this qubit? In order to redoubt it, one applies a resonant pulse actually between the levels of 1 and 2. For level 2, the tunnel barrier is very low, so the tunneling from level 2 happens fast, and again it just gives a voltage pulse across the junction. So this is how to measure it, and the one can measure probability for a system to be at the level 1. Right, so it's principle single shot measure. You have measurement result from you don't have to repeat experiment many times before you get the result of measurement. Right, this Josephson junction in principle arranging several between them, let them talk to each other through, for instance, capacity for inducting circuits. One can also think of making 2 qubit gates. Another realization which has been made in Delft and was active for about 10 years. It was so-called flux qubit. What's the idea of that? Let me spend several minutes to outline it. One can start with following setup. One can start with Josephson junction, which is in a loop of finite inductance. Let me now write the energy as a function of phase. This is the energy of Josephson junction. And this is the energy of this loop. It's inductive energy. So that also depends on phase, but in a parabolic fashion. Good. Then what do we have here? We have a parabolic term, and we add oscillation term. And if we align external flux through the circuit, if you change external flux to the circuit, we kind of can shift parabolar and oscillating function with respect to each other. So let us arrange it in the following way. Let us arrange that the maximum of Josephson energy, the maximum, comes against the minimum of parabolic potential. All right, then we just add these curves, and results are very sensitive to the inductances here and here. If these inductances are the same, they are almost compensated. So the actual result of the summation looks like this. This dip comes from Josephson energy, and the increase comes from this parabolic potential. Good. So what we have realized is a double well potential. In other courses, I frequently talk about qubits as about a particle in double well potential. Here it's practical realization of it. So what do we expect in this potential? We expect two levels due to tunneling through the central barrier between this from one well to another well through the central barrier. We can also shift these positions of the barrier with respect to each other by tuning this external flux. Right, so we can realize this double well potential with Josephson junctions. Let's see how does it go. Of course, we don't want to look at high levels. We concentrate on these two states. Right, and the Hamiltonian can be, again, it's the level system, so it should have a simple Hamiltonian. The Hamiltonian is like this. So here is something which relates to very height. Here it's something which is which can be directly related to the flux. Fine. This is flux qubit. What is important for visualization, these two states in different wells, they are related to different circulations of the current in the loop. You apply magnetic flux, and you induce circulating current in the superconducting loop. And for these two wells, these currents are just of opposite sign. In practice, it is better to make, not to make large inductive loop, but just to use two other junctions instead of this loop. And that's a practical realization which has been Delft. Right, so one needs 3 tunnel junctions for this realization. For all this, we actually need big Josephson energy. Why is it so? Because we playing with potential, and the quantization effects are somehow small. There can be also opposite limit, which I will also outline. Let's say something to say about this realization again. No, I guess I said everything. If the questions, don't hesitate to ask. Can I see the chart? I still cannot see the chart, but I kind of feel when something comes to the chart. Oh, I do see it. That worked. Fine. Let me go on and let me describe yet another type of Josephson qubit, charge qubit. Again, I would flash your picture, which you have already seen. This is about Josephson island in the regime of large charging energy. So what are the states over here? They are just charge states affected by gate voltage. And in almost all points of this parameters space, we don't have much quantum mechanics. The island in just a state with certain charge, except the crossings of two levels. Then, if the energies of two charge states have the same are the same, we can arrange superpositions of the two. Good, and there's some energy splitting for these two superpositions. Using these, people managed to realize, actually, I guess it was the first realization of Josephson qubit. Let me talk a little bit about this pioneering experiment. So that's experiment again. I don't have it frequently, so let me understand the. Let me give you some experimental details. So it was a box, single electron box, and island. Here it is on a circuit. Right, that box can be affected by gate voltages, right? That corresponds to motion in this direction for the diagram. And of course, there has to be some Josephson coupling with the box. That can be also changed by applying flux in this loop. And one had to have a possibility to read out the state of the box, and that has been achieved by some. See what will happen. Great. This qubit, sir, I don't dare zoom anymore. The box is here. So what one can do, what was the idea of this experiment? It was manipulation by DC pulses, as we discussed before, very fast one, non-adiabatic. What was the working cycle? What they wanted to do? So it is a setting of gate electrodes. This is this axis of discharge. Good. So there was a crossing of two levels, as I showed in the transparency. So initially, the setting was here. And in this case, the qubit is surely in the state 2. They make a pulse and bring it right at the position of anti-crossing. What will happen to the qubit? If you did very fast, it's still in the state 2. Now, this Josephson energy, one can see as a magnetic field. So the qubit will become to rotate around this axis, x-axis, in this basis. Fine. We stop the rotation after time delta t. We bring the system back. And now there is a readout coming. If the system is in a state 0, and if you come back with this voltage setting, it will be here, and that energy is big enough for a quasi-particle to tunnel out of that junction. So one has an electric signal. Good. So what do they make experimentally? It was very simple. It's not one-shot measurement, which one can do with this, but one can just repeat this manipulation, this measurement many times, right? Changing the duration of a pulse. In this way, one sees oscillations of the current as versus time of the signal versus pulse duration. And these oscillations are related to oscillations between these two levels, to rotation of a qubit between these two levels. Good, so it's not so much to do with this qubit. One cannot make it as practical and flexible as Josephson qubits, but well, it was a pioneering experiment. Let us see how much time do I have. Well, quite much. Let me tell you about next step in making qubits. This is a device which Leo de Carlo made about 10 years ago, and the main structures of this device still stays the same. It was a realization of two-qubit processor two Josephson junctions. So it is essential in this scheme that qubits are put to a resonant cavity. Resonant cavity also has advantage that all other frequencies which are not as resonant have difficulty to come to this box, to this resonant cavity. And one can use this resonant cavity resonance as a way to read out the qubits, as a way to manipulate the qubits, and one can make this quantum processor. This is an example. Let's see if I can zoom safely. Not sure. So if it crashes again, it will be too bad. It's a combination of Zoom as its communication program and actual Zoom which you are doing. Right. So here we have the cavity, we have resonator line. Here there are junctions representing the qubits. As you see, they're quite big, and also the qubits are separated by rather big spacing that you need to achieve microwave resonance. Good. 2-qubit processor on Josephson junctions. I don't remember how much Leo Di Carla is today. That can be like 32, something like that. I don't follow, well, frankly, because it became already very technical. I can hardly see simple physics in that. But, well, it has to be, because after all, this technology should be practical, should bring some practical use. It doesn't have to be physics. Good, sir. Still have time to talk about spin qubits. Right. What was the idea? The idea was how to say, rather, I shouldn't have say retarded. It's not very polite to say so. But in fact, it was like getting back to basics. Since spin is the most practical implementation, since electron spin is the most known and simplest implementation of the level system, let's use electron spins for that. What do we have to do for this? First of all, one needs to isolate electrons, right? If you talk to many electrons or so many spins, you just cannot see anything. Right? A convenient way to isolate spins are, of course, quantum dots. So, for instance, in these quantum dots, one can achieve trapping of two electrons with different spins here in this quantum dot and in this quantum dot. Right. How to deal with this? Handles for spin are just magnetic fields. So in principle, one needs to manipulate magnetic fields and apply it at high frequency to achieve manipulation of single qubits. One can couple these qubits as it is shown in this figure. So what is the idea here? I guess I have something on this transparency which I'm not showing, or is it next transparency? Right, in this setup, the electrons can be brought close to each other, and then there is exchange interaction between their spins, and that's a way to provide interaction gates and ultimately CNOT gates. Okay, that's what I put. I have to put the next transparency. Again, the same setup, 2 quantum dots over here. Right, there are leads to change the number of electrons in the dot. There are contacts which can eventually read the charge in the dots. And this is a way to read the spin eventually. You just arrange tunneling rates in such a way that they depend on spin. So, for instance, electron goes out only if its spin is up. Then you see it as a change of charge, which you can detect with a quantum point contact over here. Good. I guess I explained the basics of spin qubits. Well, they exploit kind of different topic, different lecture, this course. They exploit quantum dots. Good. Basically, that's it. That's what I wanted to tell you today. Are there any questions? Concluding questions? Oh, that's again the question, the chart. Why do I miss it today? I have so many technical difficulties today. All right, chat. Slide 24. Oh, Jesus. 24. This one. Perhaps there's some other enumeration. Yeah, I guess you mean this slide. Yes, right. So electrons are transferred by two. Josephson junction provides Cooper pair transfer. Does this answer your question? All right, good. So thank you for your attendance. Thank you for keeping up this course. Although it's online now, I hardly feel your presence, but I still do feel I appreciate this. See you next time.